Hi folks, we're back from spring break and we are looking at 5.2 normal distributions, the empirical rule, and some examples on how the empirical rule works. All right, so what's a normal distribution? So what ends up happening a lot in statistics is we have some sort of histogram that is a relative frequency histogram. So like we're looking at relative frequencies. In other words, we take each one of the bars in the histogram and we divide by our total number of items in the sample or total number of items in the population, whatever. And it ends up making this kind of smooth red curve that you see here in red. That's like a bell curve. All right, and we call that a density curve. So I'm not going to test you on that, but that's technically what it's called. It's a density. It tells you like what portion or how thick or how dense a certain section is. Like higher is more dense, lower is less data values, less frequency. All right, so when this curve becomes a very special shape, we call it normal. All right, so some things about a normal curve. The area under the normal curve, so if we look at the area under this red curve here, or the other area under this bluish curve here, is equal to exactly 1, or 100% if you want to work at it as percent. All right, this normal curve is exactly symmetric. So one side here matches the other side here exactly. So 50% here, 50% here, here's the middle. All right, mirror image. All right, the mean equals the median equals the mode. So the mode is always at the highest point. So you see where it hits the highest point? So that's where the most data values are, right here. All right, so that's our mode. It's also our median because it's 50% below, 50% above, so it's right in the middle. And it's also our mean. So we sometimes just label it with the little, our mu there. All right, and this is sometimes also called a bell curve. So you've probably heard the term bell curve before. That's a normal curve. A normal distribution is a type of bell curve. All right, so now for each mean and each standard deviation, whatever numbers you want to choose, there is a different normal curve out there. So like here, we've got this red one. It looks like its highest point right here. If we go straight down, is at 0. So that's its mean. All right, its standard deviation, well, it only goes from like here to here, it looks like. So it doesn't look like it's very wide. It's very narrow. It's very tall and skinny. All right, so this one has a small standard deviation, and if you look over here, its standard deviation is actually the square root of 0.2. All right, you don't need to know that. That's okay. All right, if we look at the next one, say the green one. So I'll use green here. So the green one here is also centered. If there's its highest point, if we come straight down, it's centered at 0, but it's a little bit wider. So like it goes out farther in each direction. You can see it goes out to at least 3 in each direction. So it has a larger standard deviation. And if we look, this one was 0.2. This one is now 1. Of course, these are variance, not standard deviation, but it doesn't matter. All right, the next one if we look at the blue one here, again, the blue one is very wide, but it still looks like its highest point is right there at 0, so its mean is 0. But it's really super wide. In fact, it still hasn't hit the axis or still hasn't gotten really close to the axis by 5 in each direction. So it's very spread out. It has a large standard deviation. And finally, if we look at the pinkish one here, I guess I'll have to use purple. It's shifted over here, so its mean is down here at -2, and its standard deviation looks to be somewhere between the red one and the green one, all right, because of how high it is and how spread out it is in each direction. So it looks like it goes up maybe 2 or so and down maybe 2 or so. All right, but for any mean and any standard deviation, you could come up with a normal curve, all right, and you could center it at that mean and spread it out using that standard deviation. All right, so what we do is we take all these different normal curves and we can kind of scale them down to be the same normal curve. And that same normal curve uses z-scores and is called the standard normal curve. So when we scale things to the standard normal curve, for the standard normal curve, the mean ends up being 0 and the standard deviation ends up being 1. In fact, the green one here is our standard normal curve. All right. You don't have to be able to recognize it by picture, but that's what we do is we use z-scores to change these x values, the mean values, and the standard deviation values into the standard normal curve. All right, and then once we do that, we can use what's called the empirical rule. All right, so the empirical rule has 3 parts to it, part 1, part 2, part 3. So part 1 says approximately 68% of the data of the observation fall within 1 standard deviation of the mean. Part 2 says it's approximately 95% within 2 standard deviations in each direction. and part 3 says 99.7% within 3 standard deviations. All right, so very, very important 3 parts right here for our empirical rule, but we can put them all together using symmetry and some other properties to get this curve right here. All right, so here's our empirical rule curve right there. Now the question is, how do we get these percents, like 34 and 34 and 13.5 and so on? So here's the mean, like here's our z-score down here, 0. The red numbers here are z-scores. So if we're going from 1 standard deviation down to 1 standard deviation up, so between here and here, that should be 68%, right? That's what the empirical rule says. All right, well, if we split that down the middle at the mean by symmetry, 68% divided by 2 gives us the 34% and the 34%. So that's where we're getting the 34% from. All right, next up, if we go down 2 standard deviations and up 2 standard deviations, that should be from here to here should be 95%. All right, that was the second part of the empirical rule. Now, if we split that into 2 sections, like divide that by 2, what is that, 47.5%? So we should have 47.5% from there to there, and then 47.5% from there to there. But we've already got 34% right here. So if we subtract that 34%, what we end up getting is in this little section, and in this little section, we get 13.5%. So that's what that comes from. It's that minus the 34 gives us 13.5%. All right, finally, the same trick works here if we go out 1 more standard deviation. So if we go out 3 standard deviations in each direction, so from here all the way across to there, that should be 99.7%. That's what the empirical rule says. All right, well, we can split that in half, right down the middle. And if we split that in half, we get, what is it, like 49.35%. All right, now we've already counted 47.5% in the first 2 sections, the 34 and the 13.5. So if we subtract that 47.5, all right, we should get 2.35%. Or the numbers are off here somewhere. I did something that messed up. Oh, it's not 0.35, it's 0.85. Is that 85? Yeah, 85 sounds right. All right, but we should get 2.35 in here, in this little section here. And that leaves this little bit left over of 0.15 and 0.15 in each thing. Now, you don't have to memorize how to come up with this stuff. And I'm going to give you this chart. You just have to know how to use it. So this is how we use this chart. Let me switch back to a color here. All right, so this is what your problems are going to be like. So suppose the mean weight of an adult golden retriever is 70 pounds, and the standard deviation is 6 pounds, and weights are normally distributed. So I'm telling you that we have a normal distribution with a mean of 70 and a standard deviation of 6, and this is normal notation for that. What's the probability of one weighing between 64 and 76 pounds? So we got a couple things we could do. The one I like to do is just start with the 70 pounds, the mean, and just put it right here in the middle. All right, now our standard deviation is 6. That's what we're going to count by. So we go up 6, and that's 76, and then up 6 more, and that'd be 82, and then up 6 more, and that would be 88. And this way we go down 6. So if we subtract 6 from 70, we get 64. Subtract 6 more, and we get 58. Subtract 6 more, and we're at 52. All right, so now we don't need these numbers in between. That's just how our curve works. So again, if you want to use z-scores, it'd be 0, 1, 2, 3, -1, -2, -3. That's how many standard deviations above or below the mean it is. So 64 is right here. 76 is right here. And between those two numbers, we have these 2 sections. So our answer here would be 34% plus 34% is 68%. So roughly or approximately 68% of these adult golden retrievers will be between 64 and 76 pounds. All right, let's change colors here and do the next one. What's the probability of one weighing between 70 and 82? All right, so 70 is right here. 82 is right here. So 70 is between these sections. It's right in the middle. It's the mean. 82 is right here. It's between those two sections. So we get this guy right here and that guy right there. So we're just going to add up 34% plus 13.5%, and that gives us 47.5% as our answer. All right, the last one here. Let's see what color. We'll go down to red. What's the probability of one weighing less than 58 pounds? So 58 pounds is down here. There's our 58 pounds right there. And we want to be less than. So that's this direction. So that'd be this section and that section. So that's 2.35% plus 0.15%. And if we add those up, we get exactly 2.5%. So it would be approximately 2.5% would weigh less than 58 pounds. All right, let's try another one. Last one here. So suppose that the mean time for a mile run is 8.4 minutes. So there's our mean with a standard deviation of 1.2 minutes, and that times are normally distributed. So that means we've got a normal distribution with a mean of 8.4 and 1.2 as our standard deviation, mean standard deviation. All right, so if we want, we can label it on the curve here. We could say, okay, this is 8.4, and if we just keep adding 1.2, this would be 9.6, 10.8, and this would be 12. And if we keep subtracting 1.2 in the other direction, we'd have 7.2, 6, and this would be what, 4.8? Mine's somewhere in here, by the way. All right, so what's the probability of having a time between 6 and 10.8? So 6 is right here. 10.8 is right here. So between those two numbers are 1, 2, 3, 4 sections, and we've got to add up all those. So 13.5 plus 34 plus 34 plus 13.5, or you can just think back to the empirical rule. This is 2 standard deviations down. This is 2 standard deviations up. So this adds up to 95, and it is a percent, so it would be 95%. All right, the next one. What's the probability of having a time between 7.2 and 9.6? So 7.2 is right here. 9.6 is right here. So between those are these two sections of 34, or that's just 1 standard deviation each direction. And the empirical rule says 1 standard deviation each direction. 34 plus 34 equals 68%. All right, and the last one here, having a time more than 8.4. Well, 8.4 is right here in the middle, and we just want to go up from there. All right, well, the middle breaks it into 50-50. We got 50 on each side. So this would just be exactly 50%. If you wanted to, you could add up the 3.4, the 13, or sorry, the 34, the 13.5, the 2.35, and the 0.15, but that would just get you exactly 50%. All right. So that's how we do problems with the empirical rule. So check out the homework. Hopefully you can get that done without too much trouble.